Well, hello everyone, and welcome back to Adrian's Digital Basement 2. What we have on the bench is the Magnavox Color Monitor 40, which I recently showed off on the main channel. This was one of the monitors that I worked on, and this monitor is actually an amalgamation of two monitors. The Color Monitor 40 for the CRT in the front of the case, but the board and other parts of this monitor actually come from the RGB Display 80, which is a higher resolution monitor, and unfortunately its CRT was scratched, so I decided to use the high resolution board with RGB, in this case with this vibrant and not scratched and not worn out CRT. Now what I want to do in this video is I want to start the modding process for this monitor, and in the main channel video when I talked about this monitor I mentioned that I wanted to do some mods on this. Now this monitor as it sits right now has composite video and it has TTL RGB. That's it. It doesn't have luma chroma, and it also doesn't have analog RGB or SCART. Eventually, I really want to modify this thing where it gets the full complement of input. So I want to add the SCART jack to it with analog RGB support. And I also want to, I think eventually I want to mod this thing where it also has luma chroma. So basically turn this thing into a 1084. Although as it sits right now, it's going to have a low resolution CRT, but otherwise it'll be like a Commodore 1084, just in a different case. Now, if you haven't watched a video on the main channel about these monitors, I recommend you do that first, because there's a lot of background information about what makes up this monitor in that video, and I'm just knocking stuff over with my chair. This monitor, while it doesn't look like a Commodore 1084, internally is a Commodore 1084. It's just a bunch of components were removed by Philips when they made this to disable a bunch of the extra features. So to restore functionality back, to add the RGB and the luma chroma, as I talked about, a bunch of components that will need to be installed on the board. That's not what I want to do today. If I turn the monitor on, and sorry, the microphone's going to pick up a bunch of noise and CRT whine and stuff like that, so it's not going to be ideal, but the VIC-20 is hooked up to the machine, or to the monitor that is, and if we open the door, one thing that makes this monitor different than the 1084, well, at least when it comes to the controls that are on the front, all the knobs are the same here, and it has an RGB switch as well. But this monitor also has a switch on the front that when I push it, and I just need to hold the board in place because the back cover is removed right now, it changes the display to green. Now it also has the effect of disabling the color, so if we go to diagnostic mode on the Apple IIc, there's normally a color display here of stuff. And whoops, that was the wrong button. There we go, the color is back. So as you see, yeah, it just basically makes it green, I guess text mode, green text mode. I don't really know the point of this, but that's what this button does. And as far as I'm aware, all of the Magnavox Philips monitors that don't have luma chroma, so just they have regular composite video on the back only, seem to have this button. So if you have one of the variants of this monitor with this button, then the mods I'm going to do in this video totally apply to whatever monitor you have, and you should be able to do the same mods. All right, so we're going to look at the schematics in a second and look at how this button actually works. But one of the things I find is, like, I think the button is silly, it's useless. All it has the effect of doing is disabling the blue and the red, and it also just has the effect of turning the color or the saturation all the way down, like that. I feel that that's sort of useless, and what I would much rather it do is when I push the button, I would like it to do two things. I would like it to disable the color like it's doing now, so that's fine. But I don't want it to make the screen green. That's just silly. It should just be monochrome or, you know, shades of gray. But also what I'd like it to do is disable the filtering that happens on all color composite monitors that's required for color video, especially in NTSC. Everything over like 3.58 megahertz is basically filtered out, and that contains critical information that creates sharpness in the video signal. And that's why when you hook up any computer like an Apple IIc, which is really just a monochrome computer, when you're in text mode like we are here, it's just not that sharp. All right, so here's an example. I've zoomed in a little bit. This is just 40 column text, and there's no color, which is why we don't have any color fringing. But notice the text is just not that sharp. And yes, I'll give you that this is not the sharpest CRT. I'm using a television grade CRT, but it could be a lot better than this. And if we go to 80 columns mode, which I think I could do by doing that, the text is really soft. I'm asking a lot for 80 column text on a television grade CRT like this, but if I put this board into its original chassis with the higher resolution CRT or the lower dot pitch, it would still look really soft. But it's soft because there's a filter applied. So let me jump to the schematics and let me talk a little bit more about this filtering and what I want to do exactly. All right, I want to try to do my best to try to explain what's going on with this filtering exactly. So when you think about composite video, you probably are under the impression that it's pretty soft and fuzzy. Well, let's go back in time a little bit to when NTSC video was first a thing. The original TV signals in North America were broadcast before color existed. So they were black and white signals. It was just luminance information that was going from the transmitter to your television. Now, because it was being broadcast over the air, there were bandwidth limitations for how much bandwidth the video signal could take up. So therefore, the resolution that I think originally was supported was something like 300 lines across. And that's because there were filters applied just to make sure the bandwidth of the signal, which takes up part of the radio waves, didn't exceed the allocated bandwidth that was allocated to your TV channel. I'm not really doing a great job explaining that, but essentially in North America, I think you have 6 megahertz for a particular TV channel, like channel 3, and your video signal needs to fit within that. And if you have too much information or the resolution is too high, the amount of space that's taken up in the broadcast band is going to be more than 6 megahertz, which is not allowed. So the TV stations filtered the video signal before it left and went through the transmitter, so it fit within their bandwidth allocation. That created a video signal, even though potentially the display that was receiving it could display a higher resolution, you never could get that higher resolution over RF connection. Well, think about the fact that inside a television set, the RF signal is received and converted into a composite video signal, which is essentially a luminance signal, that's the brightness information, that's the actual picture you're seeing, and some sync information that's encoded together into this composite video. Well, there's nothing to say that that luminance information couldn't be higher resolution. And if you've ever used an old computer, like an Apple II, hooked up to a monochrome monitor, you'll know that even over a single composite video cable, the 80-column text is very sharp, very, very sharp. In the 80s, those monochrome monitors you could buy, like from Zenith and Apple and whoever, they could typically handle and easily display clearly 600 pixels across, 700 pixels across, even 800 pixels across. Obviously, the Apple II's resolution is like 5 something by 192. But when you're talking about resolution on NTSC video signal, we're not talking about the number of lines. There's always the same number of lines. It's roughly 480 lines of visible display, and that's interlaced. So if you're running in non-interlaced mode, like from a computer, 240 is generally what you're always going to have. That's fixed. Can't change that. But the horizontal resolution, that is not fixed. This is just an analog signal as the beam sweeps across and it's turning on and off that beam. Well, if you want to turn it on and off faster, if the monitor can do it, the amplification in the monitor is able to handle that, and you're able to, well, send a signal to the monitor that's transitioning that signal very quickly, like you're using output drivers and transistors that can change that state very fast, well, you could have 1600 pixels across by 240 lines, and that is completely acceptable. In fact, I think the Amiga ECS chipset and up has a 1280 pixel across mode in NTSC and in PAL, and then the number of scan lines is fixed, whether you're in NTSC or PAL, respectively, the number of lines you have. Now, when they added color, they needed to fit that color information into the same space in the broadcast spectrum. So for NTSC, the way they added color is they just overlaid a high frequency pattern, let's just say, on top of the luminance information. Now, this is a big oversimplification again, but they did it in a way that when you display a color video signal on a monochrome monitor, one that doesn't have color decoding, the only side effect of having color in the video signal is you just see a kind of a subtle dot pattern on top of the shades of gray that you're looking at. And if you've ever looked at a VCR plugged into, say, an Apple II composite monitor or any other high-resolution computer display composite monitor, you will know those dots that I'm talking about. Well, on a color display, what happens is there's an extra IC that decodes or looks at those dots, and based on phase angles and all this, that, and the other thing, and of course PAL works a little bit differently, but it's very similar in the way it encodes the color. It turns that back into color information that then is overlaid on top of the luminance or the brightness information. So you have this brightness, which is the black and white picture, and then you have the color information overlaid on top of that. Well, that dot pattern or that color information that's encoded into the video signal is up at the high end of the resolution. It's up around 3.58 megahertz, which is the color carrier for NTSC, and PAL's actually a little bit higher at 4.43, which is why PAL overall has a little bit higher resolution than NTSC. Well, when a color display, like this one, is hooked up through composite video, even though the color information is being decoded by a special color decoder chip in here, and then it's mixed back in to the overall picture, the luminance information to give you a nice color display, you would still see that dot pattern if it weren't for some filters that they install in the monitor that filter out that high frequency part of the video signal. So the filter that's in here is essentially a low pass filter. And what that means is only the low part of the information can pass through the filter, and everything above a certain frequency and up is just removed. Or it's not actually removed, it's attenuated, so the signal level gets much weaker. So that has the effect when we put text through the monitor that has that filter in place, even though it's in monochrome mode, that filter is always applied on a lot of monitors, like especially this one here and all these Philips ones. So it just has the effect of softening that text. And 80 column text is much higher frequency than the color information, and therefore it's completely filtered out and it's just like a smeary mess. And that is unfortunately one of the negatives of using a color television or a color composite video display like this with an Apple II. Now what Atari did first, when their 8-bit line of computers and then Commodore, is they decided to separate out the color information from the luminance. And they would send that from the computer to the display with two separate cables, luminance and chrominance. And if you've ever heard of S-Video, which kind of came around with the Super VHS era of things, so a bit later than the Commodore 64 and the Atari, of course, it used the exact same methodology, and then DVD players did as well, and game consoles and things like that. Well, when you separate out that color information from the luminance signal, you don't rely on that dot pattern in the luminance signal to decode the color anymore. What happens on monitors like the Commodore 1084, when you switch the monitor to luma chroma mode, it disables that filter on the luminance side. So all of the high resolution information in the text is actually passed through to what you're looking at. It's no longer filtered. The 1702, by the way, does exactly the same thing, and any television that has a YC or S-Video input does exactly the same thing. The luminance information shouldn't have those filters applied, therefore it's much higher resolution. And that's one of the big reasons why S-Video is higher resolution when you use a game console or a DVD player with it or a Super VHS, is that filtering has been removed. So you've broken free of that bandwidth limitation of around like 300 lines of horizontal resolution that you would get when that filter's there. And now you could display, if your TV is capable of it, 720 pixels across, which is what a DVD player uses, for instance. Now, a good number of computers back from the 80s didn't have the ability to display luma chroma or S-Video or YC, it's all the same stuff, right? Apple II didn't have a way to separate the video signal. In fact, the color on the Apple II relies on artifact color, and this is like a side effect of that way that decoding of the dot pattern works, that if you even draw vertical lines, which is what the Apple II does, and it adds a color burst, which tells the display, hey, this is a color video signal, it has the effect of decoding these monochrome signals in color. And that's because color NTSC it's just a monochrome signal with a dot pattern, which happens to be the color information encoded into it. It's because it's backwards compatible with monochrome displays. That was the whole point of that. So the Apple II, instead of drawing a nice dot pattern, it's actually just emulating the color using these vertical lines, and you change the phase of it and that changes the color. Anyways, long story short is that when you have an Apple II in color mode, when you look at regular text, which is single pixel wide, well, you get fringing around the text. In other words, the risers on the letters can be green or purple, and that's because the resolution outputs from an Apple II happens to match exactly the color frequency of NTSC. That was Woz's design to allow the artifact color to work. And the side effect is you get that fringy color. So if you take an Apple II and you plug it into a Commodore 1084 or 1702 and you switch it to YC mode, and you just have the video cable plugged into the luma input on the monitor, while it's in separate mode or YC or LCA mode or whatever you want to call it, all the same thing, the text is actually quite sharp. And again, it goes back to what I was talking about with that filter. It's disabled. Now, because of 1084 or 1702, when you switch it to luma chroma mode, it's expecting the color information to come over that separate chroma input. Well, the Apple II doesn't have that. So when you plug the composite video into the luma jack on the back of the monitor, you switch it, you get nice, sharp, high-resolution text, but it is all in monochrome. Even when you go to graphics modes on the Apple II, No color is decoded on those monitors. Well, the mod I want to do here is I want to change the green switch on this monitor to essentially get rid of that whole green mode. I think that's silly. So just go to monochrome. So the equivalent of turning the color control all the way down. But I also want to modify this monitor where pushing that switch also disables the filter on the video signal. So it has the effect of giving us high resolution monochrome text through the composite video input. And really just, it's going to replicate the functionality of the 1084 or the 1702 when you switch it to luma chroma, but you're only plugged into the luma input with something like an Apple II. That's what I want to do on this monitor. And I think the mod is going to be super simple and won't require, I don't think, any extra parts, I think. And that means if you want to do this mod to improve the resolution of your monitor like this that has this green mode to make it a bit more useful, you can. So let's go to the schematics and try to figure out how this green switch even works in the first place, and then how I can hijack it and use it for my own purposes to give us high resolution text. Here are the schematics for the 1084. And the funny thing is, this is a really high quality copy of the schematics, but the weird thing is what's in this book, which obviously was issued by Commodore and scanned by someone, isn't the schematics for the 1084. It's actually the schematics for this monitor sitting right here on the bench. The one without the analog RGB and the one with the green switch on the front. So we can kind of look at this to try to understand the way this monitor works versus the 1084. Now, actually, I misspoke. It's not exactly for this monitor. And if you notice, it's listing a whole bunch of different part numbers for different monitors. Okay, so when we look at the schematics, kind of ignore those part numbers there. We look over here, CM8505. So the color display 40 that I have, that the CRT here comes from, but not the analog board, that was all rusted out. The one I actually had was a CM8502, not an 05. And the funny thing is about this 05 version is it has a comb filter, which is this delay line circuit that actually improves the decoding of color quite significantly with NTSC. It's not in either of the monitors I have. It's not in the 1084. It's not in this one, which was the 8564. And it's definitely not in the 8502, which was the rusty board. Not in any of those. Now, when the comb filter is installed, the switch for luma chroma on the back of the monitor is actually this comb defeat button or switch. But anyway, this particular monitor has RGB analog, RGB digital with the conversion board, and it does not have chroma input. Okay, either way, it doesn't really apply because we don't have that exact monitor. And we look at this schematic, which it says it's for the CM8562, and this is the CM8564. So we do not have a chroma input. There's no comb filter at all. And this is the TTL conversion board, TTL RGB. There's no analog RGB at all on this monitor, like the circuitry is not installed. And that's it. Yeah, this is pretty much the schematic. Now, I was always confused looking at these schematics because the 1084 is neither of these. 1084 has the chroma input and it has both RGBs. And I'm like, where's that schematic? Well, recently, after searching a while, I found another copy of this same high-res schematic. And when we look down at the bottom here, there's some additional pages. Like this was always the last page in the PDF I had. And then there's this additional page, I don't know, has some more Commodore part numbers or something. And then it has this really low res copy of the schematics here. And this has the chroma input. So there's the whole circuit for the chroma input. And that's the RGB switch. Somewhere on here is a switch. Oh, there it is. LCA or Luma Chroma or CVBS. So that's the composite video, baseband system or whatever that stands for. That's the composite video / Luma Chroma switch. That's the one on the back of the monitor on the 1084. Anyhow, we have the schematics here so we can kind of look at the way this all works. So it's nice to finally have a copy of the US 1084 schematics. It took a while for me to figure out that that's what this exactly is. And I've confirmed against my 1084 that these are the right schematics for the Philips monitor. Well, let's go back to the schematic that matches this monitor and let's try to figure out how this green switch works. Okay, so there is SK4, that's the green switch. There's two parts of it. That means it has two rows of pins. This is half of it. Half of it is for disabling the blue and the red drive that goes to the CRT. Essentially what's happening is the composite video chroma information comes into this. It's an NTSC color decoder. Out of this comes a component-like signal. Basically, if you know component video, it's got two color connections and then a luma connection. That's what's coming out of this chip. So this is the chroma signals that come out of this chip. Now, if you had a PAL monitor, This would be a different chip for PAL decoding, but the same color information would come out of it. There's like B minus Y and R minus Y or something like that. That goes into this IC502. And what IC502 does is it takes that component color video and converts that into RGB, because that's what you need to drive a monitor with. Well, so if you could follow this along, out of this comes the RGB video signal. It doesn't even say RGB on here, but you happen to know if you kind of look over here, there it is, RGB. So this bottom row of transistors and whatnot is the drive circuitry for red, green, and blue. So if we follow that green switch, you'll notice through these diodes, it's connected to there, which is the blue, and down here, which is the red. So when you push that, it essentially has the effect of disabling the output of these two drive circuits. And that just means that all you're getting is green. Now, I mentioned this in the first video about this monitor, that normally if you did that, well, if you were displaying like red on screen and you disable the red, you're not going to see anything, you'll just see black. Well, the other half of the SK4 green switch is down here. And if I zoom in a little bit, what this has the effect of doing is canceling out the color control on the monitor. So the color potentiometer on the front, you can turn it all the way down where you have a monochrome signal, all the way up to like a ton of color. That's going into this matrix decoder chip. And when you hit that, it grounds that out and basically is the same thing as just turning the color control all the way down. So that's really why when you push the switch, things that are red still have a bit of a shade to them, because the color control was turned all the way down. So the color decoding is essentially disabled on the monitor. Now, so to disable this whole green functionality of it turning green, all you have to do is stop 12 volts from getting to these two diodes. Now, I happen to have looked on the actual physical monitor, and it turns out from the switch, before it gets to these three resistors, there's actually a little jumper wire, a piece of wire that's installed on the board, probably because there was no room for the trace or whatever, so they actually have a wire there. Just removing that wire will simply have the same effect of having the switch in the open position. So open position, it's not connected to 12 volts. Taking the wire out has the same thing. That will completely disable the green thing from happening altogether. Now down here on the color side, I actually like the fact that it turns the color decoding all the way down. I want to keep that. So what I want to do is I want to reuse this part of the switch up here that I'm now not going to use for green to disable that filter that's on the Luminance signal that takes away that resolution and makes the text really fuzzy. And I haven't really talked about that in a second. Let's go look at that. Now, because it's just easier than me scrolling back and forth a whole bunch, I happen to have a copy of the PAL 1084 schematics, and there are substantial differences on here. But then there are a lot of similarities as well, and it's just much clearer to look at than the NTSC one. So for this part of the circuit, it's exactly the same, so we can use this. So there is the switch, the LCA and CVBS switch. Now, when you have a 1084 with a separate chroma input, extra components are installed. All of this stuff here is not there on this monitor. And if we go back to the schematic, this transistor, TS514, this is actually the video input signal. So composite video comes in and it's all buffered through all this stuff here. And this lower connection to TS419, that's sync information, so we can ignore that stuff. But this is the actual color and luminance information that's making its way over to the rest of the circuit. Now it splits right here. You see that joint. On the lower trace is the luminance information. This is the actual brightness info that's making its way to the video decoding and all that kind of stuff. And it's the top path up here on this schematic, that's the color decoding. So there's some filters and stuff here, which I think are designed to only pass the color information. It tries to filter out the rest of the picture. And that makes its way all the way, we follow this, makes its way into IC501. That's the NTSC color decoder. Notice that the luminance information on the bottom here, it doesn't even go into that chip. If we kind of follow it down, it comes down here and it goes over here and it makes its way right into that RGB matrix chip. And that's because the NTSC decoder is decoding the color information, and it comes out as component information, goes into this IC502, and it also needs the luminant information. It leads luminance and then two color signals. And that's these three inputs, 15, 18, and 17. So right now we can ignore all the stuff that's happening on this top row because we're not going to be touching the color decoding whatsoever. That would be for later if I'm trying to mod this thing to have YC. In fact, we go back to the schematics for the 1084, the PAL version, it's the same. There's the chroma input, the chrominance input. There's resistors, and then we have these two transistors. One of the transistors is actually handling the color information that's coming through the composite video, and the other one is handling the chroma information or the color information coming through the separate jack. And the switch here Now, it doesn't quite make sense what's actually happening here. I think there's an error in the schematics. I've found other mistakes, but at the minimum, what it does is when you have the switch set to composite video, it disables this transistor, the one that is buffering the chroma input. And then when it's enabled, it actually turns on that transistor, so that means that it's driven by the chroma input, and then that makes its way down here, and it goes into TDA 4510. That's the PAL decoder, so it'd be a different part number on the NTSC monitor, but essentially all of these parts here, these transistors, these resistors, the switch, this stuff here, and I think this resistor is all added to support chroma luma separate mode versus just regular chroma. On the regular version of the monitor like this, doesn't have that separate input. TS514, the signal comes out of that, the luminance and the chrominance signals combined comes out of that. One part of it goes up to the luminance signal up there, and the other half goes from that joint right there to basically that joint right there, bypasses this stuff because that's not even populated on this board, and then that feeds the chrominance information into the color decoder. Where I'm going with this is this switch, when you push it, has the effect of doing two things. It's switching the chrominance information to either come from the chrominance jack or the composite video, but the other half of it, this half on the right side, goes over here to this component, S533. This signal here where I'm running the mouse over, that is the luminance path. That is the detail, the actual picture information where the text, everything we're looking at, not the color, but the actual black and white image, is this path. Well, that inductor, it's a variable inductor and it's got a little capacitor inside. It looks like when that part is grounded, and unfortunately, they're just so bad the way they draw this stuff. The way this switch is when it's in the CVBS position, the out position, is it's connected like this. Now, is these two pins and those two pins are connected. So now this is a signal for ground. See this line over VBS? That's ground. This pin, which goes to that whole drive circuit for the transistors and stuff, which we don't need to worry about, that's grounded. And this pin is grounded as well. And that pin, when it's grounded, makes its way over to here to this inductor S533. And remember, I was saying that when you have composite video, you need to filter that high frequency information out of the signal. Otherwise, you see a whole bunch of dots on top of the color. So grounding this inductor actually turns it on, activates that filter. Now going back to the switch here, and I'll switch to a different color. When you push in the button, then those two pins are connected and those two pins. So what I've drawn in blue. Well, there's nothing connected to that pin there. Now, remember, the left side has to do with the color transistor stuff. We can ignore that. This is 12 volts, but whatever. That pin right there, that pin's not hooked up to anything. It's just floating. And that means when you push in the switch to luma chroma mode, this S533 is just not connected to anything. And that has the effect of disabling it. Okay, so now we know for the 1084 to go to high resolution mode, we have to take away the ground that goes to this inductor. Now this is where things got a little weird. We take a look at the schematic for this monitor, or one that's pretty much identical to it. There's the inductor, S533. It doesn't show it connected to anything. So the dotted line around it and the ground that's there, that is the case, the actual case of the inductor. This is a little inductor that you can stick a tool into and turn. That's grounded. But the connection, it shows it floating. Well, we know that's impossible because if that were floating, that filter would be disabled. And for sure, it's enabled. It looks fuzzy and everything. And you know what? I went and actually checked the board. I took it out of the monitor, and sure enough, it is actually, through a jumper link, it's grounded. So I don't understand why the schematics show it not grounded, but it's a mistake. And I think it's one of many on these schematics, unfortunately. So now we have kind of a plan. If I want to make it where when I push that button in, it sets the monitor to monochrome, so it's like turning the color down, that's half the switch. I'll leave that alone. But the other half that makes the whole screen green, well, I don't need that anymore, right? I don't want that. So what I think I'm going to do is I'm going to modify that part of the monitor, that half of the switch, which is normally disabling the red and the blue drive. And we're going to hijack that and use it to essentially switch the ground in and out for that particular filter, which should have the effect of giving us high resolution text when we push that button in. And there's a few cool things about that. In the Apple II world, sometimes you're in a graphics mode that is not designed for color. Like it's just strictly monochrome graphics mode, but there's no selective way on the Apple II to disable the color burst. In other words, to tell the monitor that's connected, hey, this is not a color signal, so don't try to decode color. As soon as you turn on graphics on the Apple II, the color burst is going to the monitor. That means the monitor is decoding color. So you have to force the issue in the monitor, on the monitor side, to get a high resolution image. On a 1084, that's easy. You just push the Luma chroma button. It's on the back of the monitor, unfortunately. If you push that, you'll get high-res text. It's monochrome. You won't get the artifact color. Look, well, with this monitor, with this mod, we'll get that same functionality, but even better, the switch will be on the front because it's the green switch. And instead of going green, you'll just go to monochrome, and it should give us high-res text. And again, caveats, with this CRT, it's a low-res CRT, so it's not great. But if I had the original CRT, the scratched one, in here, then it would be able to display that text very clearly. 80-column text, no problem with that CRT. And we would be able to go to a graphics mode, like double high-res, and have no artifact colors. So it's kind of a win-win, and I'll show a couple demos of that once this mod works, if it works. I'm sure it will work. Okay, so I've written up a little bit of instructions here, and I'm going to, of course, post this with this video. So if you want to do this mod yourself, hopefully this is clear enough. But SK4, that's the name of the switch, the green switch. High resolution monochrome Luma mod. So as I mentioned already, I'm just kind of reviewing what we talked about here. One side feeds 12 volts to disable the red and blue drive via diodes D604 and 605. That's just, we saw that in the schematics. But the other side disables the color decoding on IC502. That's by turning the color all the way down, right? So the mod is all of these steps, and the only thing you're going to need is a couple pieces of jumper wire, and you have to be comfortable cutting through some traces, because we're going to have to do that. So we're going to remove a jumper wire that goes from triangle 48 to 27. That's the green wire that is near the switch. I talked about that. That sort of hooks that switch up to the whole part of the circuit that disables the, it makes the whole screen green. We're going to cut 12 volts that goes to the switch itself, to SK4. We're going to cut a trace between the two pins, because the way it's hooked up right now is 12 volts actually hooked up to two pins. We need to cut the in-between of those as well. Should be no problem. We're going to remove a jumper link at 9252. That's what turns on the filter. And that jumper link is not shown on the schematic. I mean, it shows it floating here, but the reality is there's a jumper link that goes from the bottom of this to over to ground. And we're going to be removing that. So that's 9252. And I actually wrote what it does. This normally grounds coil S533 all the time, enabling the filter. And then we're going to run a jumper wire, so just a piece of wire, from the middle pin of SK4, PCB edge, to jumper link, or the pad of jumper link 9252 on the PCB edge. And actually, there's one thing I forgot to mention, or maybe I didn't put it on here. Okay, yeah. When we cut that 12-volt trace that goes to SK4, that's for that green mode we're getting rid of, you need to ground that pin. I'm going to actually put that on a separate line, because I missed that just now, right? So yeah, cut 12 volts going there. We're going to ground that pin, and then we're going to cut the trace between SK4, between the two pins that were normally grounded. This will make sense when I kind of show it on the monitor in just a second. And then we run a jumper link from the middle pin of SK4 over to the same pad of 9252 on the PCB edge, and that should have the effect of selectively disabling the filter on the luminance signal, give us that high-res mode. And of course, that switch will, the other half of that switch will still turn the color down to give us a monochrome mode. This mod will have the effect of turning on the Luma filter when the green switch is out, which is just the normal operating mode of the monitor. When you push the switch in, it will disable the filter, giving you a high-res Luma signal without the filter. And also while it's in, it has the effect of turning the color control all the way down. So it gives you that monochrome mode. So that's it. Pretty easy. It's just like a couple pieces of jumper link, I guess, and no parts, and should improve the functionality of this monitor, at least in my opinion. Now, to do this mod, you don't even have to take the monitor apart beyond taking the cover off. Now, if you're not comfortable or you don't know how to do that safely or work inside a monitor safely, don't do this. I really don't recommend opening a monitor unless you know what you're doing. Now, if the monitor you're working on has the shield removed already from the bottom, and I already did that on this monitor in the last video, then you can do this mod entirely right here. It's in this whole section of the board. I take that back, actually. The one filter is under the plastic, so you will need to take the monitor apart. Okay, so back to what I was saying then, if you don't know how to discharge the CRT and be all safe about it, then don't do this mod. Incidentally, this monitor's been off while we've been going through the schematics talking, and there was about 6,000 volts stored in the CRT still. So these monitors seem to kind of self-discharge to some extent when you turn them off, but it obviously still retained 6,000 volts. That's enough to give you a pretty big zap. Oh, by the way, I forgot to mention, I fixed the power LED on this monitor. It wasn't working at the end of the last video on this monitor. Well, it turned out that the LED was completely rusted, which matches because the whole board had a bunch of rust all over it, and yet the LED was totally rusted. So I did replace it with a red LED because I think that looks better anyways. And I'm glad I did it because I already left this monitor on once for several hours. I was using it upstairs, playing Nintendo games. I shut the Nintendo off, and I left the monitor running for a while. And I only noticed later because I was like, oh, it's really hot still. Oh, it's on. Oops. So yeah, I decided I needed to fix that power LED. It was a pretty easy fix. The hardest thing was I had to take a regular square or rectangular LED and sand it down because the opening on the front of the monitor is really small. And the other thing was the rusted legs on the old LED were really hard to remove because when metal rust, it expands. So I couldn't get it out. I had to drill the holes out on the PCB. Anyways, that's all fixed now. And now it has a red LED anyways, which I think is kind of unique because all these monitors have a green LED, which I don't know, doesn't look as good. I like red better. Okay, these are the two switches. This is the green switch. It's on the edge of the board. This is the volume control. The amplification circuit is there, so it kind of gives you a little orientation. This is the front of the monitor. Yep, green is the furthest one on the outside. This is that jumper link I talked about, the green wire that goes from the switch over to here. And this makes its way through some other traces, I think over to this section here, and that's where the disabling of the red and the blue, red and the blue happens. So if we remove this wire, simply removing that wire should just disable that part of the functionality as well entirely. Now this part here is S533. That's our filter. This is the part that is causing the blurry text that is enabled all the time. And the hilarious thing is this in the schematic showed it not connected, but there's that jumper link 9252, that jumper link, which is installed on top of resistor 533, that's what's keeping this thing enabled all the time. And if we remove that jumper link and don't do anything else, that'll disable the filter and it will always have the higher res text, but then we'll always get that dot pattern, which is not ideal. We do not want that. Okay, so here on the back side of the board, there's S533. That's our filter. That's the jumper link that's installed. That is grounding. So this is ground up here, and this is keeping it grounded all the time. This trace that runs off that direction, that's actually going to the luma chroma switch and the comb filter defeat on the front of the monitor. We're not using that switch. I don't have a hole in the monitor, so I can't use it. But that would not be installed, or maybe a resistor is installed there actually, when that switch is in use in the front of the monitor. On the bottom of the board, it's resistor 533, same number as this S thing, but I don't see that resistor in use. Because if we go over here, there's the LCA switch, that goes right to ground. That resistor is not in use on this schematic at least. Yeah, that's a little bit odd. There must be another monitor configuration that has that in use. Oh, you know what? Maybe it's the version that has the comb filter. Let's take a look at that one. There's S533. Oh, there it is. Ah, interesting how this is a little bit different. So there's the comb filter defeat. In the normal position, it's actually connecting this filter to ground through a resistor, and when you push it in, it's fully grounding it, so it bypasses that resistor. I think that has the effect of partially disabling this filter, not entirely. And I think that's just really because the comb filter doesn't work as well as S-Video or Luma Chroma input. There's some filtering you still need in place. So this is the comb filter right here, the delay line. So I assume that resistor allows the filter to be partially in place or fully in place, either grounded or partially grounded. So removing that resistor entirely, just letting it float, like on the 1084, completely disables it, which is what we want. We want that for this mod. All right, time for the mods. So there's the switch. This right there that I have the pointer on, that is the green wire on the other side. That is connecting here to there, and that goes off to the resistors and the rest of that circuit. I'm going to just desolder that and that, pull that green wire out entirely, and then I'm going to remove this jumper link 9252 entirely. And then down on the switch again, these sides closest to the edge, this is the stuff we're disabling. This is where we're doing our mod. Well, this trace right here that goes to there and there, that is 12 volts. So I'm going to cut right there. That's going to isolate that stuff. And then notice how these two pins are connected together. I need to cut in between those as well. And that's because I'm going to be running a bodge wire from right there, that middle pin, over to this pin on S533. Well, I can use where the jumper link was installed right there. You could do it on either, it's fine. And then after cutting the 12 volts, I just need to find ground right around here, and we're going to need to hook that pin up to ground. This might be ground. I don't know, we'll figure that out in a second. Okay, this is warmed up. Let's get this wire out of here. There's the wire pulled out on one side. It's zip tied, so I got to do it from the other side to get that out. And let's get the jumper link out. You know, when Philips installed this stuff, they kind of bent these jumper links over, and it can make it kind of annoying to get them out. Sometimes you just have to use a little screwdriver to try to tilt that up a little bit. All right. See, it's moving around there. It's out. There we go. There's that jumper link. And I just cut a zip tie so I can pull this green wire out. There it is. There's the green wire. So that's the green functionality disabled. And right now the filter is disabled all the time. All right, I have my little mini Dremel tool here so I can start cutting through these traces. Trying to figure out the best way to do it. I'm going to do it over here. So I need to check in a second that I cut through there, but that's one, and then I have to cut between these pins. Sometimes when you're doing this work, it can be hard to see. So a little IPA can cut down on the amount of dust. Okay, we got the multimeter. Let's double check that this is actually not connected. Good, not connected. I left a bit of a gap there for the 12 volts, simply because I wanted to make sure that it wasn't ever gonna, make a connection or something. So if I want to re-enable this functionality, I just need to put a jumper link there to there, back over here in those two positions, and reconnect these traces. That's all I have to do. It's pretty easy. Still connected, come on. Oh, it's probably because the button was in the out position. That is why. Let's try again. Okay, now it's not connected. Now these two are connected. Yep. Now we're going to leave that floating because when this is in the in position, remember, we want this to be floating. We don't want this to be grounded anymore. We only want it to be grounded when this is in the out position. So I'm going to connect this pin, which was connected to 12 volts. I'm going to connect this to ground now. Now, if I connected the ground to that pin, it would be inverted. So when you pushed it in, we go to monochrome mode, and then we would actually have the filter enable. So we'd have low res text, and in the out position, then we would have the filter disabled, which is not what we want because out is color. Now, because I want to make sure we have a nice solid ground going from this ground point with the switch over to that component, I'm using a nice thick wire. And this is a solid core wire, so I'm just gonna kind of route this down. I will stick this down with some glue later. That's good enough for now. So there to there, we have continuity. Currently the switch is in the in position, so it's that pin, which doesn't go to anything anymore. It went to where this green wire used to go to. And when we have it in the out position, that's gonna ground the component, which of course doesn't go anywhere right now because I cut the trace. So I need to connect that pin to ground. Let me just find a ground again. I think it's this. Yeah, there's ground right there. Oh, you know what? That's a ground pin. That's actually the case of the switch body. Yeah, right there. Yeah, I'm getting 0.28 ohms. I think that's a pretty good ground. Okay, just a little piece of offcut there is all I need to make sure that's grounded. So now if we go there and I connect to ground, it is currently grounded. And if I push the switch in, it is not grounded, it's open. And that's exactly what I want. So switch out, we want the filter enabled. So it's grounded, in, we're looking good. Okay, one thing I am gonna do is put a little nail polish over that copper that I exposed. There's a little bit of copper right there in the corner, so I'll do that. And theoretically, I should put some here too. There we go. That's because when I cut the trace, I expose a little bit of copper. So with this lacquer, that makes sure there's no issues in the future. Okay, with that, we're done with the high resolution monochrome mod on this monitor. Now I need to put this back together and we can test it. All right, monitor's back together. I'm gonna turn the Apple IIc on. Call -151, we'll do an L. I have the green mode disabled, so we're just in standard composite video mode. I'm gonna turn the monitor on. Here we go, hopefully we don't let the smoke out of something. If there's a problem, I can fix it, I would imagine. Okay. All looks good, all looks good. Reset, color's working, good, we're looking good. And let's go into call -151 and do an L again. Okay, and there's 80 column text. I should probably zoom in so you can see this a little bit more clearly. How do I get back to 40 column mode? There we go. Okay, I guess that's how it looks. Let's do a quick test. GR. Okay, there's a color fringing. We're in graphics mode. We go back to text, if I typed it correctly, and we would have no more color fringing. Okay, I'm going to push the button. Let's see what happens. It certainly didn't do anything obvious. Is the text any sharper? I'm not sure, actually. Let's do a diagnostic. Oh, yeah. Oh, yeah. So you can now see vertical lines in all of the gray, and that's because the filter is disabled. So if I turn down the, well, let's turn the color back on, and let's turn the color manually all the way down. Now we don't see any lines there, and when I push that, lines become evident. Hopefully that's showing up in the camera. But yeah, that's definitely better. There's also a sharpness or peaking control. We can turn that up. Text looks a little sharper as well. Yeah, the text is definitely looking pretty sharp. Let's go to 80 columns mode. Oops, that's not the right way to do it. Yeah, I mean, that's a big difference right there. Okay, so watch when I push the button now. Okay, well, okay, the difference is not as huge as I would have thought. So with the button pushed in, definitely the 80 column text is a lot more readable than it was, without a doubt. And yeah, without a doubt, we can definitely very clearly see all the lines that make up the low res color mode there. And I push the button, and of course we have the color control. Oops, that's the wrong one. Color control, there it is. Sharp, high res, color. And if we go into one of the graphics modes, we of course don't have the color fringing text anymore. If we turn the color back on, now we do, now we don't. So it's a great way in graphics modes on an Apple II to get sharper text and sharper graphics without that color fringing. All right, well, I'm kind of annoyed. I can't find my Apple II desktop disk. It's a graphical operating system for the Apple II, and it looks absolutely horrible when you have a color monitor. So I'm going to boot up a game. Yeah, good old Apple II making that headbang sound. Fat City. Of course, without the color, it doesn't look super great, but you can push the button, and now it looks really good. And there we go. Now we can see those vertical lines, which make up Apple II color. Cool. And here is the demo I think I really wanted to show off. And this was something that I remember back in the days. Music instruction set, which doesn't really use any color, so you get a lot of color fringing. And when we push the button in, now it looks awesome. So when you have the button out or using a regular television, you just get all this color fringing. It's still usable, but you just get all this purple and green all over the place. And when you push the button in, now it just looks that much sharper. Hopefully with the camera a little closer, it's just a little more obvious with some of the stuff on the screen when the button is pushed in versus pushed out. In, out. I think this was a worthwhile mod, I really do. Yeah, especially when you're using something like this with an Apple II. Huge benefit to having this button on there, in my opinion at least. Just how sharp everything looks here compared to that. It's not like it's horrible. It's still a good monitor. It does a good job at not over filtering what's coming in on the Luminance signal, but this just makes it that much better. Okay, that's going to be it for this video. I think I really want just to go through the process of figuring out how the mod would be done, like looking at the way the monitor worked versus the 1084 and seeing what we could do very easily to this monitor to give it these extra capabilities. I still want to do the Luma Chroma mod on this thing, so I want to give this monitor a chroma input, and I think I figured out a way to do it, but I'll talk about that in the video where I actually implement that mod. But I think I will be reusing the green switch on the front again, because I don't really want to drill a hole in the back, and I like that there's a button here to switch between Luma Chroma versus having it on the back like it is on the regular 1084. So it's actually a little bit better in that regard. But that mod will obviously require a bunch of extra components to be installed into the board. As I kind of talked about in the schematics, we could see the 1084 had a bunch of transistors and stuff, and there will be some other mods I'll have to do. And the biggest thing in figuring out how to do those is not just simply installing those components. There are jumper links that are installed in this monitor that are going to be different than on the 1084, and none of that is on the schematics. So I have to like trace out every component, find the components, mark them, figure out how they all connect together physically on the monitor. and install the appropriate jumper links for those components so they work the way they should on the 1084 versus the way they work on this, because that stuff is being bypassed right now. That means there's jumper links that are doing that bypassing, and we got to figure out where those are, remove them, and then install the other components. I could just take the 1084 and compare the boards. That's one way. But even that is not easy because there's a bunch of other stuff on that 1084, like all the RGB stuff that's on there that this doesn't have as well. So one step at a time. I'm going to do these mods little by little, and I think this was just the first phase. The whole disabling the filter stuff is half of the luma chroma mod already done. The other half is I would have to disable the fact that it turns down the color when you push the button, and instead of doing that, switching over to the chrominance information. It would have the same effect, though, if I was plugged into the Apple II of disabling the color, because obviously then I would only be plugged into the Luminance input, which would be the regular composite video jack, and it would look just like this. So it would work the same way. It's just we'd have now access to an extra chroma input for the Commodore 64 and the Atari and any S-Video VCR, DVD player, whatever, so it would look extra great on this monitor, like nice and high res. With this CRT, it's not awesome, but once I put back in the other one without the scratches, if we get those fixed, then it will look amazing. So I hope you found this interesting and figuring out how to do the mod and everything. And, you know, don't be afraid to play around. And it's so cool that these monitors are so versatile that I've added a feature to this that never was there originally. And now I think it's a big improvement on the way this monitor is versus, you know, the way it came out of the factory. That is an improvement in my book. That really is. And it was easy. 2 pieces of wire, cutting a couple traces, easy peasy. So if you like this video, thumbs up. All the usual YouTube junk names scrolling up over here, you know, subscribe, etc., etc. Let me know what you think about this. I think people don't love these CRT videos, but I love working on these things. It's super fun to me. And that's going to be that. So stay healthy, stay safe. I'll see you next time. Bye.